Welcome everyone. My name is Roy Petrakis. I am a geographer with the Western Geographic Science Center of the U.S. Geological Survey in Tucson, Arizona. Today the title of my presentation is Harnessing Remote Sensing Data to Support Ecosystem Restoration on Tribal Lands. So for this presentation today, I'll discuss two projects in which we used remote sensing data and applications to address resource management challenges on the San Carlos Apache Reservation. So both projects that I'll discuss today take place on the San Carlos Apache Reservation, located in east central Arizona. The reservation is located roughly 100 miles east of Phoenix and northeast of Tucson, Arizona. The reservation has a land area of approximately 7,500 square kilometers and a population of roughly 15,000. So with this land area and population, there's a fairly large amount of open land. Additionally, it's home to a very diverse and dynamic landscape. For instance, as shown in the images on the right, the vegetation ranges from desert scrub in the lower elevations to ponderosa pine forest in the highest elevations. Additionally, there are large grasslands and pinus juniper woodlands spread throughout the reservation lands, and though not shown here in these images, there's also mixed native and non-native riparian forests within the reservation, primarily along the river bottoms of the San Carlos and Gila rivers. So one of the primary resource management challenges within the San Carlos Apache Reservation, and truly extending throughout the entire western and southwestern United States, is a growing risk for larger and more severe wildfires over the past several decades. Though this graph is slightly outdated, both the numbers of fires and overall burned area is increasing generally year to year, and many factors are driving this, including a long history of fire suppression throughout our forests, as well as drought, changes in seasonality, for example, earlier springs or longer summers, and rising temperatures. On the landscape, fire severity can have significant impacts. For example, fire severity is intricately tied to carbon release, the extent and scale of post-fire recovery is dependent on severity, and the ability of both native and non-native species to respond following a fire can also be dependent on how the fire burns at the time. However, forest fuel treatments have been shown to be effective at reducing both tree mortality and burn severity. These themes were the inspiration behind this first project that I'll talk about today, which was to assess the effectiveness of various fuel treatments on fire impacts. Our research questions were, how do burn severity and post-fire stand dynamics vary among fuel treatments, and what are the management implications from these fuel treatments? So ultimately, what did we learn? So unfortunately, I don't have time today to get too much into the weeds on the various fuel treatments, but I did want to introduce the remote sensing methods that we use to answer these questions. So first, to measure fire severity, we use the Difference Normalized Burn Ratio, or DNBR. This index is commonly used to discriminate between burned and unburned vegetation. It provides a quantification of remotely sensed burn severity, particularly for the canopy. So essentially, it's a metric of remotely sensed burn severity and may differ slightly from on-the-ground conditions. To produce a DNBR product, we developed pre- and post-fire NBR images using the near-infrared and shortwave infrared bands and Landsat images. You can see the NBR equation listed here. The DNBR is ultimately the difference between these two images. On the bottom, we show the pre- and post-fire NBR images, as well as the DNBR image on the right. So you can see slightly higher severity in the lower half of the 2013 Creek Fire. Red would indicate higher fire severity, as well as pockets of some high fire severity in the northwest up here and southeast corners, although this area here had the highest fire severity throughout the entire fire. Burn severity can give us an indication of what fire conditions were like on the landscape at the time of the fire, but we also need to quantify the post-fire vegetation response. So to do that, we use the multi-temporal Kauff-Thomas, or MKT transformation. This is essentially a multi-date tasseled cap transformation. We produced a pre-fire MKT product, as well as a 1-year post-fire and 3-year post-fire product to measure response over time. By measuring the difference between the pre and post-fire images, we can see the post-fire response following the wildfire. So 3 main metrics are produced when using the MKT transformation: delta brightness, or delta B, which can give an indication of bare soil or in a canopy space, dark charcoal, for example, following a wildfire; delta greenness, or delta G, which is an indicator of vegetation growth and overall productivity within the vegetation; and finally, delta wetness, or delta W, which measures soil moisture and overall vegetation condition. So again, similar to the DNBR slide before, in the map on the bottom, we show each of these indices 1 year post-fire. So you can see where the highest fire severity occurred in this area. So with delta brightness, there's a large increase in brightness 1 year following the fire. And with both delta greenness and delta wetness, you see a large 1 year decrease where you have the highest levels of fire severity. So when looking at burn severity by treatment type, we see some interesting patterns. In this map, red represents higher fire severity, so in the map on the left. For the mechanically based treatments, harvested and harvested thinned here in the middle, we have more red, or higher fire severity. More yellows occurred within these areas. For the areas that had some sort of fire-based treatment, resource benefit burn, RB, as well as harvested prescribed or harvested RX, we see more blues, generally with some pockets of red, but generally lower fire severity within these areas. This is also represented on the graphs on the right, where fire-based treatments had lower fire severity on average on both gradual and moderate slopes when compared to both untreated areas as well as the harvested and harvested thinned areas. You can see that here, lower fire severity on both gradual and moderate slopes. When looking at the MKT metrics, so the post-fire response, we can start with greenness here. You can see a strong linear relationship between burn severity and change in greenness over time. So as burn severity increases, greenness decreases at essentially the same rate, which was expected. As fire severity increases, you see a reduction in greenness. Now looking at wetness, the results are very similar to greenness. As burn severity increases, wetness decreases. However, it decreases at a slightly greater rate with increasing burn severity. So you can see that on the graph here, where higher fire severity experienced a greater rate in the decrease of wetness both 1 year and 3 years after the fire, right here. So in addition to wildfire, the western U.S., including the San Carlos Apache Reservation, has been experiencing drought conditions over essentially the past 2.5 decades. To illustrate that, these are precipitation anomaly maps produced by the PRISM Climate Group at Oregon State University at 5-year intervals. So these maps will generalize across 5-year periods and may not show some of the contrasting short-term precipitation anomalies which have occurred. However, they do represent general long-term conditions. So on this first graph on the left, from the late 80s to the 1990s, mid-1990s, this region in general experienced above average precipitation with positive anomalies at roughly, this appears to be about 130 to 150% of average. So it was wet during this period, though this map only shows November 1990 through October 1995. However, beginning in the mid-1990s through present day, this region has been experiencing negative precipitation anomalies or below average precipitation. For example, from 1995 through 2000, precipitation was roughly 70 to 90% of average. Similar conditions were present from 2000 through 2005, 2005 through 2010, 2010 through 2015, and finally 2015 through present day. So ultimately it's been relatively dry, below average precipitation over the past 25 years for this region. So drought is a significant driving theme behind a new project that we've recently begun assessing riparian vegetation transitions within the Upper Gila River watershed, which is along the border of Arizona and New Mexico. There are 3 core aspects that we are researching in this project. First, we are completing a historic analysis in which we are mapping changes in the land structure and vegetation from 1935 to present day. Second, we are quantifying more recent trends in vegetation conditions from 1984 to present day using Landsat and other imagery sources. And finally, we hope to make conclusions on the relationship between what we are seeing with the remote sensing methods in the vegetation with climate and drought. So is there a relationship between these? So historic aerial imagery is truly a great way to look back at conditions from the past. A similar approach, using the same aerial imagery from 1935 that we'll be using, was applied to map woodland change across the reservation by my colleagues Barry Middleton and Dr. Laura Norman, who are also co-authors on this presentation. Using image analysis, they quantified the amount of woodland tree and shrub coverage in 1935, and then again in 2017 using using NAPE imagery at 3 areas across the reservation. So ultimately they observed large-scale increases of woodland canopy coverage in 2 of the 3 locations, and you can see that here in the table on the bottom. From about 18 to 38% in the B flat location, 18.3 to 38.5, and from roughly 28 to 43% in the Bloody Basin area. So both of these areas experienced large-scale increases in woodland canopy coverage. In addition, savannas were also more prevalent across the study area in 1935. So overall, these results truly inform restoration applications, and we're able to learn about the landscape from 1935 using this imagery. So it's very useful. We propose a similar analysis to study the change in riparian vegetation cover along the Gila and San Carlos rivers. So in this map, we have the 1935 imagery on the left and present-day high-resolution NAPE imagery from 2019 on the right. We can analyze the imagery to identify various characteristics of the vegetation, such as density and composition, as well as the location of primary and auxiliary flow channels. So in this first location, we see a likely transition from both vegetation type and density from a more typical riparian savanna, where large flows could historically wipe out much of the vegetation in 1935, to an open grassland with pockets of high density vegetation in 2019. So you can see that here, there's a high density vegetation and a much more savanna-like landscape in 1935. In the second location, we see a transition from largely unvegetated area in 1935, possibly a former flow channel, into a more dense non-native vegetation stand in 2019, right here. So it's very, very dense vegetation, where it used to be a lot more open in this particular area. So these are the types of conclusions we hope to make using this analysis. So the second core objective of this project is to assess more recent conditions in the vegetation. Products within this analysis are both spatially and temporally explicit and show pixel-specific results over whatever time period is under consideration. So we're using the SendSlope trend in Google Earth Engine to produce these results. One of the main challenges in assessing trends over time is that trends are dependent on the time period that they cover. So for example, one area can have an increasing trend for a particular period of time with a decreasing trend even within a subset of that same time period. So to account for that, we are assessing trends across various multi-year periods. For example, how do conditions vary between the wet period from the 1980s to the mid-1990s to drought conditions over the past 25 years, or the past 2 decades? So those are sorts of time periods we'd like to look at. Additionally, we're focusing on specific events such as wildfires, floods, vegetation die-offs or transitions, for example, from native to non-native species, and things like that. So we also hope to look at seasonal trends, where phenology of each vegetation type can vary and would vary seasonally. So fire is not only occurring within the upland vegetation, but also becoming more prominent within the riparian areas. Several large-scale fires have burned in recent years along both the Gila and San Carlos rivers, and in both native and particularly non-native vegetation. We plan to use remote sensing to look at various aspects of wildfire within the riparian zone. For example, the tamarisk beetle is expanding throughout the upper Gila River watershed. So this is a product produced by River's Edge West showing the tamarisk beetle spread over time from year to year. So as of 2020, using this distribution map, the beetle was not quite at our location. It was still a little further east from where the study area is. However, recent unverified observations from this year suggest that it may be even closer at this point. So the beetle ultimately defoliates the vegetation, which may increase fire risk. Additionally, vegetative drought or transitions to non-native vegetation species may be leading to an increase in fire conditions. These maps show an increase in NDVI from the summers of 1994, 2000, and 2008 over large areas, which would indicate transitions to non-native tamarisk stands and a large increase in overall density of the vegetation. When NDVI reaches above 0.6, 0.7, 0.8 during the summer, that's likely an indication of non-native vegetation. When this is coupled with drought conditions, these areas may be at greater risk for wildfire. Or it may be something else, and that's something that remote sensing hopefully will be able to tell us ultimately. So overall, remote sensing applications can inform resource management challenges. It's a very useful tool and has been very effective in these applications. It can protect culturally sensitive resources or even culturally sensitive areas, and that's very important for where this work is taking place. Both for fire and fuel treatments, fire can be an effective treatment type, and we are able to show this using remote sensing applications. And this is for both natural and prescribed fire on the landscape. And then for drought and vegetation response, riparian areas are experiencing complex transitions resulting from climate shifts. And remote sensing is able to visualize this in different ways. So we're excited to see the results ultimately from that project over time and see what we can learn from that. So on that note, I just wanted to say thank you. Quick acknowledgements. This research was conducted with support in part from both the Land Change Science Program of the Core Science Systems Mission Area of the U.S. Geological Survey and the USGS Southwest Climate Adaptation Center. I want to thank everyone who's involved in this project and their hard work. So my contact information is listed here, so don't hesitate to reach out if you have any questions. Thank you.